The first lecture, I want to just sort of set the stage. I want to explain what a moduli space is, what a classifying space is, and stuff like that, and through a series of examples. Then the second lecture, I'll talk about the moduli space of lattices, which is something we understand much better in the moduli space of curves, but for which there are still a bunch of open questions, so I'll try to highlight some of them. And then the third lecture, I will talk about the moduli space of curves itself. So this first lecture, I'm very broad audience of topologists, so I'm going to try to start very gently. This is moduli and classifying spaces. And I want to begin with the easiest moduli space you can possibly think about. So what is a moduli space? Well, the word was introduced by Riemann in the 19th century. He was trying to figure out what parameters do a Riemann surface depend on. So the word moduli means parameters. And so what these are supposed to be is they're supposed to be spaces that parameterize some geometric object. And so the easiest geometric object that we could try to understand is the space of triangles of perimeter 1. Okay, so that's something that you learned about when you were small children. It looks something like, such a triangle looks something like that. And how do we specify one? Well, we have to specify, of course, its 3 sides, which you might as well call A, B, and C. So the first attempt is, well, call the space M sub triangle. I'll put a tilde there to indicate that that's the space we're looking for. What is it going to be? Well, I have to specify 3 sides, so B and C. And so what are the sides? Well, the better first they be positive, right? So A and C are all positive. They also have to satisfy the triangle inequality. And there's 3 different triangles. We need A plus B is less than C. We need A plus C is less than B plus C is A, and then finally this condition that the parameter is just normalization condition. That just means that A plus B plus C is equal to 1. Okay, so this is a space you could draw, right? And so this is itself, you notice, a triangle, right? So this, what is it? Well, or at least it's the interior. Yes? You want to flip those inequalities? I probably do. Look, you're not going to get a correct statement out of me. That's not real. I'm going to make technical mistakes. Most of them are designed to be lies to entertain you rather than, So what is this? Well, as I said, it's a triangle. Space, I'm going to draw it like this. The 3 corners, well, we have points, 1, 0, 0. Here's a point that's 0, 1, 0. Here's a point that's 0, 0, 1. Now, there's a central point right here, which corresponds to the, so here is the equilateral triangle. The point, well, since they're supposed to have length 1, so it's 1/3. 3 sides. We also have some other special points here. So we have these ones right here, and also these ones right there, and right there. And those correspond to some special triangles. Let me see. So this one right here is supposed to be the midpoint of that. So that's the point 1/2, 1/2, 0. This one right here is the point 0, 1/2. The point, the other one, so that'd be 1/2, 0, 1/2 right there. And so those correspond to, and this is true for the orange ones. So, and these, those are, I call those isosceles. So, where you have two sides that are equal. So that side and that side are equal, but that side, it's different. I really should have drawn that longer and skinnier to make sure that was clear in the picture. Okay. Good parameter space. So every point in this corresponds to some sort of triangle. We do not include the boundary. The boundary would be some sort of degenerate triangles where one of the sides has become 0. And we have all these special points in there. Okay, so now that I said is the first attempt at a parameter space. It's one you've been studying for a long part of your life. Last point, this is not really what we're looking for. Not really. So M triangle tilde, so the sides are of a triangle order. Right? So I've given that we have sides A, B, and C, right? And they have an ordering on them. And to specify a triangle, a triangle doesn't have canonically ordered sides. And so we have an action of the symmetric group on 3 generators that acts on M tilde twiddle by permuting the sides. And the space. So the correct space, the one that really does just parameterize triangles in a one-to-one way, is this where we take the quotient. So it's just M triangle, which is equal to M triangle tilde action. Okay, so what does this space look like? Well, we're going to see it based upon here. If make sure I put my colors so I have the right ones here. So it has, so it looks like the bottom, which is not included.
And can I just
Yeah.
I'm a little confused about the A plus B bigger than C close to like the points, the vertices of the triangle.
Oh, maybe it should be A plus B. Well, so the vertex, you mean this point right here? That's not in the space.
Yeah, but like close to that, it's still A plus B is smaller than C.
Let's see here. A plus B is bigger than C here, right? Because we have like a small one, like 0.999 plus 0.0001 is greater than 0, right?
But 0.1 plus 0.1 is not bigger than 0.8.
Where did I get this thing?
Should they maybe be 110 with
Oh, let's.
No, the coordinates right.
Where did I get these things wrong? Definitely, like the sum of two sides of a triangle is supposed to be, greater than or equal to the sum of the third, right? Or greater than the sum of the third.
I feel like you need to cut off some of like the right statement.
So this, so here is something that I know is true. Is that it's like this, there's an equilateral triangle. You have three distinct sides right there. You can go to the boundary in two ways. You can make two of the sides, you can make the smaller two sides have the same length, or the bigger two sides have the same length, or you can make all three have the same length.
But the boundary should be where it's actually aligned where the three edges make a line.
Where the three edges make? Okay. Let me, pretty sure correct is a correct picture of the moduli. So let me continue. So there's some observations about the space. So this right here, singular space. So it doesn't include this boundary point right here where we have degenerated the triangle so that two of the, one of the sides has length 0. But here, interior is an actual manifold, right? You can vary, you have 2 degrees of freedom at every point. But when we quotient out, you have fixed points of the action of S3. And so we have singular points right here, the middle point, that's the fixed point of all of the entire S3 action. And also, these two lines right there are fixed by the S3 juncture, and those become, sort of manifold, the boundaries of the manifold. So this is really a manifold with corners, right? So here are 2 points. Those right there are fixed points of the S3 right there. You're going to see lots and lots of moduli spaces are constructed like this. Naive, but it's going to impose some let's see. So the next I talk about, so will be another. So these are supposed to be parameter space subject, and so one very familiar with our so Osmanian. I'm just going to work over the real numbers. Okay, so these are supposed to parameterize k-dimensional subspaces inside R to the n, right? And so parameterize k-dimensional subspaces inside. What we could do is we could take the space of frames, k-dimensional frames in Rn, and what is that? So this time, so this is the set of all. It's going to be. We're going to call these things V1 up through Vk. These are supposed to be points inside. We're going to take R to the n such that the Vi are linearly independent. Okay, so this right here is an open subset of R to the n to the k. This is open. Why is it open? Because the complement, what's that going to be? It's going to be the closed set where all the k by k minors of this matrix are 0, right? So this is so this right here is something very easy to parameterize. Every k-dimensional subset of Rn can be, corresponds to some point in the space of frames in many, many different ways. Corresponds to choosing a basis. Riemannian gr of kn. We take the space of frames and we mod out, there's a natural action of R on there. And something we know about this, this is the Grassmannian, this is smooth since the action so there are no fixed points of the action. But now, so this is a familiar construction right there. So we have some sort of naive parameterization. We quotient out by the symmetries. Even better, I'm going to go to the mixed media part of this presentation. Where I switch to using this right here. One that. Contained, of course, in a natural way. Okay. So we add on a 0 to the end of the frame, right? Right there, and so then we can define Grassmannian of k-planes inside R to the infinity. There's the union as of gr of. And you could write this also as a quotient of, you take the frames, k inside infinity, and you still mod out the action of glk of R there. And so what's one property of this that's very familiar to topologists is that f k to the infinity is contracted. Why is that? Well, if you think about it, so the inclusion here, so you can homotope so the inclusion, well, how to say this? So it can homotope this in far well, so I should not conclusion the identity part. The identity from the frames in K infinity to something like the frames inside. Well, it's going to be K planes, but now saying I guess my notation's not great, so that's as infinity. That should correspond to r to the infinity. I'm just going to say the frame plus r to the infinity. Okay. Right there, where this means we're just at the beginning of things. You just sort of line, right? You can move frames to that, so which then can then be contracted to just simply a canonical point r to the k plus 0 k to the infinity side r to the infinity. So this right there for a fixed is not contractible. It has a very interesting topology actually. But when we let k go infinity, what this becomes is we take this contractible space of parameters, we mod out by this group action, this nice free group action. Okay, so we're going to see something like that happen in other contexts. So let me see, make sure, where did I put my, oh, there's where I put my notes. So let's see here. So, okay, so now what I'm going to do is I'm going to define for the first time the moduli space of curves. It has the right homotopy. Not for any of you that know about the moduli space of curves is going to be very offended by what I'm about to do, but that's fine. So, even though it's being recorded, I might get canceled. Going to do here. So I said this is the example of Grassmannians, and so let's now look at the example of, this is going to be surfaces. And well, I could do Rn, but I'm going to go all the way to infinity. I'm going to look at surfaces inside the infinity. Okay, so let's see. That right, I'm going to assume that G is at least 2 right now. So it looks something like this. We all know this picture. So now I'm a real topologist. I've drawn a picture, like a picture of a surface. So, and so what can I do? I can look at the space. So I want to make the observation that the same argument that I used right here, the space of K frames inside R the infinity is contractible. I just can have K0 at the beginning, and then I can just contract one point. Shows that the space of embeddings of sigma G, and these are orientation preserving embeddings, into R to the infinity is also contractible. I think there's a sort of the embedding theorem. What's the embedding theorem? That you can embed any manifold in R to the 2m plus 1. Whitney, that's the word I'm looking at. Yeah, that's the sort of panic you get when you're giving it, right? That's sort of Whitney embedding theorem. So the embedding theorem says I can embed sigma G. Well, it's a 2-manifold. But if the dimension is bigger and bigger, I can embed in, you sort of do this with parameters, and in the eventual endpoint. So, and this is like a general lesson in topology, is that a sufficiently robust existence proof will also give you that the space of choices is contractible. A meta lesson right there. And so now let's define the Grassmannian sigma G. Well, that right there is the space of embeddings of sigma into R to the infinity, and there's a natural orientation preserving, natural action, I'll step away in a second, of diff plus. And so what is this? This G in R to the infinity. So that's a very natural space. It's the Grassmann. It's the space of submanifolds of some infinite. And it's a basic fact that, in fact, so here we're using the fact that G is at least 2. That implies that this space right there, the Grassmannian, sigma G, is on the same equals, well, I'll put the equals in quotation marks, genus G. That's not a true statement, of course. We'll not tell on surfaces, it'll definitely be finite dimensional, and this is definitely an infinite. Interpreted correctly, this has homotopy type. And so really what I want to be talking about in this series of lectures is the topology of this space, the space of subinfinity, which is sort of, you know, it's a basic I like to think of it as a sort of basic topological object. Okay.
Is that actually pretty good?
Yeah, this is, that's going to be the next, yep. So yeah, this is, let me make sure I'm doing, so 10, 20, I'm actually doing slightly better for time. So, yeah, okay, so let's say that I have a, you know, an embedding of let's do sigma G, okay, into R to the infinity, right? I can then do by a straight line homotopy, I can move it so that it actually lies 1,000 coordinates every point or 0, right? Then I can perform another straight line homotopy to my bog standard sigma G inside R3, right? Okay. It's a sequence of 2 straight line homotopy. First one, and I can slide it over, so and I just by straight lines to make the first to shift the coordinates to the right. So the first 1,000 coordinates are 0. Okay, I can do that. So now that lands inside, well, this thing I slide, you know, the frames, k frames inside 0 to the k plus R to the infinity, right? And I just choose a base one whose, you know, in this case it's R to the k, and the other one for surfaces it would be like a standard R2. I mean, it's a standard sigma G lying inside R3, right? And I just do a straight line homotopy between that. Yeah. Yeah, those are embeddings, yeah, because they involve different coordinates, yeah. Right. That's right, yeah. And as long as my embedding doesn't use the first 3 coordinates are 0, right?
I mean the homotopy.
Yeah. The homotopy. It's actually it's like a homotopy through embed. Yes. So it's a fun exercise right there. Yeah. And my many times before I believed it. In fact, I was giving a talk about this at Oberwolfach, a much more complicated, even though I crashed after the talk. Come on, why'd you give that complicated argument? This is really all that's on there. So, and then I just said, okay, I'll accept the truth, whether I want to or not. Anyway, are there any other questions about this? So I'll study these things, and so let me see. Oh yeah, so I actually still have 5 minutes. So what things can we do? I want to study the topology of, and I want to make an observation that, you know, using interpretation as moduli spaces, we can construct elements of cohomology. Okay, so what do I mean? So we have Grassmannian. So you can use interpretation. Use the interpretation as a moduli space to construct elements of cohomology. I'm gonna do the easiest one. Of course, there are other ones you could do as well. The easiest one will just be this Grassmannian. We all know the cohomology of Grassmannian characteristic classes, right? But when you dragon class, you don't construct one could construct them by finding a CW structure in the Grassmannian and computing the chain complex, but that's not usually how you construct them. Usually you take a vector bundle and you do some operation to it to come up with some canonical homology class. And so we see it lies here. So there exists a so this is an example. So there exists the tautological. I'll call it T of K over the Grassmannian of K planes and R to the infinity, or Rn. I could work with either one. So, right? And so if we take so we can use e.g. Stiefel-Whitney classes. To get, say, W sub I of TK that lies I of the Grassmannian GRK, say F2 coefficients, or any other characteristic class, right? Now that's sort of stupid, like in some sense, like as I think many of you know, this actually is the classifying space for these sorts of bundles. The third lecture, I'll explain how I construct interesting cohomology inside the same idea. Okay, that's a classical construction that goes back to I think Mumford back in the early 80s. Okay, so this right here. So we have right there. So comes the next thing. This is a response to the audience saying, is this contractible? And the answer is yes, but since this is a mixed audience of topologists, I don't expect everyone knows what a classifying space is or hasn't thought about it in a while. And so here, right here, so definition. So let's say that it's a topological group. I'm allowing it to be a discrete, okay? So it's a discrete group, so examples of topological groups. They just have very boring topologies. So then, so for G, so is form. So you could say it's a space that classifies principal G bundles, but I don't want. I want to be a little more concrete. Of the form, I'll call this. So modulo G. So E, intractable space. With a free G action. This is what up to homotopy equivalence, and we write as B is equal to E modulo G. I'm just Blackboard bold G to emphasize this topological group. Okay, so what are some examples of this? So for example, so first, if G is a discrete group, so BG is a K G1 and tractable space, modded out by a free proper action of the group. Okay. So for example, we have things like this. So just to give you a few familiar examples, take S1 right there. That's equals to the classifying space for the integers. Okay. Another one there, we could take infinity, that which is by definition below the action of, I'm going to call it 2. I refuse to write D sub 2 because that should mean the 2 adducts. C2 is a cyclic group of order 2. Right to a classifying space for the cyclic group of order 2. By the way, the proof that the infinite dimensional sphere is contractible is the same proof right here, right? So they're all, there's proof. Like when you let a parameter go to infinity in a contractible space, it's always proven by the same kind of argument. Okay, so those are some other examples. As I said, this we have the space of frames, and FR, the k-dimensional frames and R the infinity are contractible, and of k-planes and R the infinity, that right there is a classifying space for G, the topological group GLKR, and the Gaussian of surfaces, that right there is a classifying space for diff plus of sigma G. Okay, because both of them are, we took a contractible thing and a free proper action. Okay, so those are that right there. So, and here's another familiar one right here. So, could do the circle that, regard. So we'll say S infinity, as set of C to the infinity. It's the unit sphere with, zero side C. So a free action of the circle, which circle inside C on the infinity. CP infinity, and so CP infinity, that is of the circle, where the circle is a just. Okay? So you see there's two different, these like goals right there. So I want to emphasize that. Okay, so those are classifying spaces, and so by definition, I guess, how do I erase, does this eraser also erase this?
There should be one over there.
I do not. Oh, left. Okay. Sorry. Okay. So, the less. Yes.
So, in your cross module example, K versus K are
Linearly independent.
but how would GLKR act on that?
No. It's acting. There's a right action. Think of this as a vector space injection, R to the K to R to the infinity. You have actions both on the domain and on the codomain. On the domain.
Okay. Oh, I see. You're like changing the parameter.
I'm changing the parameterization. I'm not changing how the span.
I thought you were doing
No, I'm just changing the basis for the vector space, for the subspace. So, what we see then, a lesson is that these things right here, these moduli spaces are often classifying. So, thus we see that, so in many cases, the ones that we're interested in. And so just a definition. So for a group G, so I just write like this. of, say, a topological group is, definition equal of its classifying space. The study of the cohomology of these moduli spaces is also a study of the topology of the cohomology of these groups. And so the groups I've talked about here are mostly topological groups. Later on, move to the land of discrete groups. Okay? So that gives you two inputs in the world. You have the world of moduli space theory, which gives you one set of intuitions, and you have the world of sort of classifying space theory and group cohomology, which gives you another set of intuitions that can sort of play off each other. Okay, so here, let me give you a non-example. So, moduli space triangles is not the symmetric group on 3 letters. Remember, the moduli space, if we take these triangles where we choose an ordering on the edges, and we have an S3 action by permuting the edges, and we quotient out by that. Since the S3 action has fixed points. And, something, this thing right here is controllable, right? And the cohomology of S3 is very much non-trivial. That's a fact that's very, it has in fact cohomology and influence, say with F3 coefficients. And so, but a basic fact. So, because in lots of cases, the moduli space will not actually come from free actions, but if a G, so let's say that G is a discrete group. And let's say that G acts on E, so, and let's say that E is contractible. So, and for all stabilizer, G sub P is finite. Okay, so this is, of course, the stabilizers are all finite, but not enough. And so then it turns out, so wall modulo G is not classifying space for G fractional. E.g., in the sense that if you take the cohomology of G with rational coefficients, that right there is the cohomology of this E mod G with rational coefficients. And so if we don't have integral coefficients, use rational coefficients, then these just go to classifying spaces. That might not be interesting, so for S3, by the way, says that H K of S3 with Q coefficients is 0 for K at least 1, because this moduli space is contractible, right? That's not the most interesting theorem in the world, since that's of course true for all finite groups, right? And you can even see it from this, that this fact encodes the fact the rational cohomology of any finite group is trivial, because any finite group acts on a single point with finite stabilizers, right? And so, it's not. So like this encodes, some basic facts about finite group theory that maybe are not obvious when you first see this. So that's a stupid corollary. Where it's not as stupid as you might think. Whereas I have different, so I keep them. So let's see, 10, 20, 30, 40. Yes, I'm at, wow, my timing on this, I have how many minutes I'm supposed to do each section, I'm exactly on time. So let me give you an example. I'll show you actually. This can give you interesting consequences. This is the because this one will be, this is one again, I think that what I'm doing now is clear to people, but yes? Oh, did you have a question? I was going to say that this is one I'm going to generalize in 2 different ways in the next lecture. So yes? Yeah. As a space, yeah. Yeah. So you can make this. You can. So if I wanted to work in the category of stacks or something, then I could actually make this an integral statement. I could say this really is a classifying stack for G, but I'm not going to do that. Don't worry. So I was at an algebraic geometry for 2 weeks ago. Started talking about classifying stacks. Experiences topologists are not happy when I do that, so I won't do it. And the whole conference, everything I'm going to talk about is going to be rational results anyway. So it's sort of whether I want to deal integral statements are just somehow not going to be not what I'm going to be focusing on. So here's an example of a moduli. So this is the moduli space of lattices in R2, and I'm going to put some words here. So the oriented lattice. So up to rotation rescaling. A lattice is something, you know, have. And a lattice, of course, we're just going to take, you know, say some points, maybe like take this one right here. So much because this is going to become much harder to draw if I keep doing this. 2, 3. This is what you always try to draw. Things become etc. Right? You know, you can start going. You know, you start take the. So it's going to be. So i.e. So a lattice is equal to the image of a linear injective map squared into R squared with that is with discrete image. I didn't write my note in a way when I tried to reproduce it from my head onto. Take a linear map. You take a an injective Z linear map from Z squared to R squared that has discrete image. That's what I mean by a lattice right here. So something like this. So I'm going to parameterize them up to rotation and rescaling. So rotation is just, if I have a lattice rotate and it's still a lattice. If I scale everything by like 7, it becomes a lattice that's like 7 times as big, right? So I want to those 2 sorts of things right here. So let me draw the thing in 2 different ways. So, what each so oriented. So let's see. So maybe I'll say it like I'll so let's consider such lattice, lambda inside a basis. So V1, V2 right there. Okay. So what can I do? Well, I'm allowed to rotate. So V2 are linearly independent vectors, and so what I'm going to do is I'm going to is equal to left. I'm trying to keep everything being stupid conventions you have to worry about here. And so it's not. Well, let's just do it like this. What I do is I rotate and to make, so first, to make V2 equal to literally the identity. So I'm R2 here as the complex plane. So I just start off, let's say that I have, two of my vectors. One of them is right there. One of them, the other one is like right. One. And so what I'm going to do is I'm going to rotate it. So this is, let me make that a little bit longer. And you rotate, rescale. I make it like this. And V1, I can make V2 literally equal to 1 at the concept of, well, I have to rotate this thing so it goes maybe in this direction right here, and it's going to get smaller, right? Because I have to scale it down to make that second coordinate be 1, right? I can do that. There's a canonical way to do that. There's only, and so now, so I've rotated the read scale equal to 1, and so if I choose my orientation correctly, so orientations, so we have 1 lies inside the upper half space H2, which is equal to the set of all points lambda inside the complex plane such that the imaginary part of lambda is positive, just like I drew right there. Now, of course, non-normal orientation, right, where, you rotate this way to make this work. Okay? And so now what do I, so thus we see that every lattice, every lattice, in our moduli space, so it can be written in the, so I'm going to, it's lambda z lying inside Yeah. This is, I want the linear fractional transformations to work out the way I want them to make out, and it's really a pain to work out perfectly. Anyway, I could write it like this. But now, so you might think that the moduli that in is actually just H2. But that's not right, because I made one non-canonical choice here. And that non-canonical choice is a choice of basis. So this involves a non-canonical basis. A non-choice of basis so base of SL2Z and the upper half, so H2 modulo SL is equal to our moduli space. I never think moduli space, and I'm going to call this thing, for various reasons, M11. M11. I should have such an, you change bases inside z squared. It's the automorphisms of z squared that the orientation, right? How does that work here? Well, this is action. Familiar action. Consider something in D take so lambda z, and now is it left action? Is it right? Am I acting on the domain and the codomain? Correct. C lambda times this becomes, well, what does rotate and rescale? Like multiplying by a complex number it rotates and it rescales, right? That's exactly. And so we can multiply by a complex number. What do we have to do? We divide by plus d. We want. So this becomes a lambda plus b over c lambda plus z plus c. Divide. You just multiply over c lambda plus make the second multiplier. I don't know, scale 1. What do you do? That scales. And so we see that this is literally the familiar action of on the upper line by linear transformations. You know, just these are linear fractional transformations. And I first learned about them, told the formula, and where does it come from? Like, that's kind of a bizarre thing to want to look at. And this is where that formula comes from. This is why that defines an action. Okay, so M1, and so right here is modulo SL2Z, and so and SL2Z, it acts so properly and with finite stabilizers. It's a little exercise right there. Stabilize any point is finite. It's going to be rotations around that point. And so what do we see is that the cohomology SL2Z with rational coefficients is the same as the cohomology of this space M11 with rational coefficients. Suppose I have 5 minutes. Close by telling you what this actually is a very familiar and easy to write down space. How do we do that? Well, if you down a fundamental domain for the we're going to do this in the 19th. So for the action. So here it is. So the thing, what are some elements of SL2Z? Well, there's the unipotent matrix 1101. That corresponds to translation right? And so what I can do is I can take the unit disk right there is, that's like negative 1/2, and that's 1/2 right there. And this space right here is the fundamental domain for the action. This here, so I'll say, so there's sort of two identifications that are being made here. Those two blue things, so the blue are identified by 1, 1, 0. Z goes to Z plus this right here. Also, there's some fixed points for the action. So there's a fixed point right there. So blue is equal to fixed points. There's an order 2 fixed point here and an order 3 fixed point right there. And then we have also this right here and this right here. So the orange, or is that, yeah, that's orange, identified by, what is it? It's going to be Z goes to, so it's going to be negative 1 over Z. Okay, negative 1 over I, right? That which fixes is the matrix. So it's going to be 0, negative 1, 1, 0, right? Has 1. So, and so just we see how they're identified. We have that's identified with that. Right there is identified with that orange. This is the fixed points. Oh, fixed. And so what's the quotient? We can just write that. We just see what the quotient is. So it's what's called the modular curve. And so what is it? So it's a like we have a right here. I should have done these. Do I have enough? Do I have an extra color? I don't have colors to do these things. The quotient looks like, so it's a punctured 2-sphere right here. We have blue right there, like this same right. It's heading out to, we have a yellow right here, right? We have this sort of seat glued up, head out that way. We also have, sort of another point, the order 3, and that right there has this sort of red thing that's glued up right there. And so this right here is equal to S2 modulus a point. Which is, of course, homeomorphic to R2. And the conclusion, then, is that the cohomology of SL2Z with Q coefficients is equal to 0 for degrees at least 1. Okay, that's maybe not the most exciting result I've taught you today, right? But on the other hand, you can see what I'm going to do in my next lecture. I'm going to generalize this from SL2Z to SL4Z and SL5Z. That's one direction you can generalize this in. And then we're going to see there's actually a very interesting cohomology that appears. And a lot of interesting terms in that cohomology. And then I'm going to, well, with mod alpha lattice, we get a torus, right? I will generalize that to the torus of the genus 2 surface, the genus 3. And I use this point of view to construct and understand cohomology classes there. And so that's going to be the theme of the other 2 talks. So thank you.